Okay guys, we're going to talk about perceptrons, and this is I'm going to try to keep this quick. It's just a summary. I'm not trying to replace class. Attendance is the best way to get this material, and this is just because we had, when we covered perceptrons in class, we had a lot of problems and missing microphones that weren't charged, problems with the camera or the projector, etc. And so you can't find this on Coursera in any helpful format, whatever. This is Frank Rosenblatt, and he invented a physical perceptron back in the 1950s. This was originally an image classifier, something that could classify things linearly, a pattern recognition device. And we saw the movie with the the photographs labeled man and woman, and the system was able to learn to some approximation to distinguish faces labeled man from faces labeled woman, even though we don't really know how we do it. We do it, but we don't know how we, and especially in the 1950s. There has been research on this, of course, but in psychology, but we didn't know how to do it. And the point is the programmer doesn't need to know how to do it to get a perceptron to learn how to do it. And that's what was exciting about this kind of system. Now, we've talked also about linear separability. I'm not going to go too much into that right now. There is a separate movie video on linear separability, and you have a characterization of it here. This is not exactly the definition, the formal definition, but you characterize it as in two space, for example. The question is, for two sets of points, can you draw a line between them? That's simply it. In three space or four space, etc., going all the way up to whatever number, then the question is, could an n-1, so for n-dimensional problems, could an n-1 hyperplane, or just think something, could that thing separate it? So in three space, the separator is going to be a plane. And after that, we can't really imagine the thing, the space or the thing that would separate it. The perceptron convergence theorem is a theorem that shows that if you do have a linearly separable problem, then there's at least one, typically some family of perceptrons, but at least one that can solve that problem given enough training. And that's important. Now notice that it doesn't say that any perceptron can do it. It just says that some elementary perceptron, given enough training, will learn to discriminate P and Q from each other. Let's look at that quickly. So here is a two-space, and P and Q are sets of points that, in fact, as you might imagine, are linearly separable. So any line here, here, or here, these all work. But a perceptron is going to start quite likely not with a line separating them. And the line, by the way, represents the, let's just say it represents the state of the perceptron at that time. So it might start with a line cutting through, say, here. And this line puts all the P's on one side. That's good, but it does not put all the Q's on the other side. In fact, it has some Q's on the P side. So it's misclassifying some of these as P's. That's not going to work. Now it has a learning algorithm that will cause it to make a correction, to try to get a better solution. So maybe the line goes over here, and now you have a line like this, or it could be like this, right? And this gets all the Q's on one side, but not all the P's on the other side. So eventually what you want, it might move around, it can shift the line, it can reorient the line, but eventually maybe you get this, right? And that's going to work. That's a solution to the problem. But remember I said not every perceptron can solve the problem. So you might have one that when it tries to get better at a problem, and we will talk about learning later, it goes from, say, here, it jumps all the way to here, and then it jumps back to here and back to here, and it just can't take that nuanced little step to go in between these two bad solutions where there's a line here and there's a line here. That's an example of something that can't solve it. But there's always going to be, as long as the problem is linearly separable, as long as the sets are linearly separable, there is always going to be some perceptron that can solve that problem. given enough training. And so that's why you just want to make sure that you remember that there's just an elementary perceptron. That doesn't mean only one, but there's just some elementary perceptron that can solve the problem. We talked also about or and. Notice these are not, of course, perceptions. These are logical, abstract logical operations, but the same algorithm can learn to solve those. These are, of course, linearly separable, as we've seen. So there's another movie video in which I talk about that, and I've done it in class, and it's in the book, sufficiently described just in the book. Now, what they can't do is learn to compute XOR and XNOR. But we're going to focus on XOR, and that's an important operation because we can do that. That's exclusive OR. Can I say, is it the case that either Anne or Betty, but not both of them, are home or is home? It's cumbersome. And if a system can't do that, that's a limitation, right? Well, meanwhile, Rosenblatt had some pretty optimistic or ambitious things to say about perceptrons. So after a press meeting with Rosenblatt, the New York Times reported in the late 50s that this was the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Now, at the time, there were other engineers that thought he was overselling it, and apparently they wanted him to kind of rein in that talk. But I think if he were alive today, he'd feel somewhat vindicated because he's just saying it's the embryo of something that will someday be able to do these things. And although it's taken a long time, we have self-driving vehicles that are being researched and developed, and they're on the streets and under certain conditions, and we expect to see more of them. We have, you might have heard of Atlas and other robots that are able to walk and balance themselves and do some pretty impressive things. Just recently, one was able to do a handstand. There's one that does a backflip. Or is it a forward flip? I don't remember. And we have vision processing, so they can see, the self-driving cars can process the environment visually and make all kinds of decisions about how to drive, where to drive, etc. They can write, they can do all kinds of other things. And no, we don't. No one's claiming to have a system that is conscious of its own existence yet. But again, this is just supposed to be the embryo of something that will someday be able to do all these things. And with the recent successes, he might feel that his perceptrons, which are the baby versions of neural networks, have been somewhat vindicated. However, back in those days, or in the 60s, there was a lot of skepticism, and the skepticism remained. Minsky and Papert wrote a book called Perceptrons in 1969, and somehow or other, I'm not trying to cast them as the bad guys, but somehow or other, this myth spread, based apparently on that book, that perceptrons could not compute XOR. Now, strictly, it's true that a perceptron, an elementary perceptron, cannot learn to compute XOR, but there are a lot of ways in which this is just a myth. And by the way, Minsky and Papert did not argue that perceptrons could not compute XOR. They just pointed out that an elementary one could not learn to compute XOR. However, engineers and others just seem to absorb this idea that they were severely limited. And imagine you're interested in artificial intelligence, whether to model the mind or to just get things to do very clever cognition and computation. If you find out that this thing can't compute XOR, if that's what you believe, you're going to think, well, I can compute XOR, so this can possibly model the mind. And we don't want a system that's that limited. So if we're not trying to model the mind, but we want something to do something intelligent, well, you don't want to use something that couldn't possibly compute XOR. So the interest in these things based on this myth faded. But it's just a myth because, again, they can be they can't learn to compute XOR, they can be hand-tailored to do so. And more interestingly, you can put them together, as McCulloch and Pitts had already shown with their neurons, McCulloch-Pitts neurons, you can put them together in ways that where they can easily learn to compute XOR and the others, right? So this was an unfortunate result, and I'd love to know more of the history on this, but I haven't been able to find much more about how this seems to have happened. To what extent are Minsky and Papert responsible for this? I really don't know. They were skeptical about perceptrons for other reasons, and so there just might have been this general attitude that people had at the time that these things couldn't, they weren't the path forward. Meanwhile, Rosenblatt dies shortly after this book is published, and the consequence seems to have been our first artificial AI winter, or specifically the connectionist winter, or one of the connectionist winters, where people shifted away, the funding dried up, and people shifted away from neural networks in general. And it really isn't revived until McClelland and Sichnowski and Rosenberg in the 80s.